Okay, let's start. I'm Dr. Badu Srestha. I want to welcome everybody to Senior Design Engine Conference on the behalf of MAE Department, WMU. Our next presenters are Jacob Anderman, Talia Hall, and Nicholas Tigerford, and their project title is Software Tool for Analyzing the Bending Strength of the Gear Teeth. I also thanks the sponsor of this project, Eaton Corporation, particularly the industrial mentor, Dr. Wing, and the faculty advisor for this project is Dr. Kim. Okay, welcome everybody once again. So group is your floor now.
All right, good morning, everyone, and thank you for attending. My name is Nicholas Tegedoff, and again, I'm here with my teammates Jacob Anderman and Taylor Hall. We're going to present on our senior design project, software tool for analyzing the bending strength of gear teeth. We'd like to thank our faculty mentor, Dr. Kim, and our industrial mentor, Dr. Wink, very much for assisting us with this project. So to give some background on the project, when designing transmission gears for reliability and long life, the goal is to create a gear tooth geometry that is both efficient and yet minimizes the stresses due to normal operation as much as possible. The area of gear teeth that is typically subject to the highest stresses is the root fillet area. This is the location where classic bending fatigue failures typically initiate. Geometry plays a large factor in the magnitude of the stress at the root fillet. Finding the ideal root fillet shape for a given gear tooth that both minimizes the stress and gives the gear tooth greater bending strength is very beneficial. So this project was done alongside and with the assistance of Eaton Corporation with the goal that the results of the project could be useful in assisting Eaton in their gear design process.
So the main drive behind creating this project is that current gear optimization processes at Eaton can take significant computer simulation, time, and resources, and is computationally expensive to perform. So we needed a more efficient and faster method to perform this optimization. If a method is very time-consuming and not a very efficient process, this can cost a company a large sum of money due to man-hours wasted, when a much more quick and efficient optimization process can be created to take its place. Ideally, a software tool where any geometry can quickly be input and have the stresses analyzed, sorry about that, while also comparing to other geometries was the end goal for the project. This would allow the engineers at Eaton to make quick comparisons for a more efficient process. The changes in gear tooth root geometry play a large part in the bending strength of gear teeth, so that is why this was the main focus of our project.
So, like Nick and Jacob said beforehand, our objective for our project was basically to create a simple yet effective software tool that the gear engineers at Eaton Corporation could use to quickly obtain an A to B comparison of the change in the root stress compared to the root fillet geometry. So when we speak about the A to B comparison, we're basically talking about accurately predicting the increase or decrease in bending stress based on the change in root geometry. So for the software tool, we used Microsoft Excel as our platform due to the wide availability of the licenses and user comfortability. So because of the COVID-19 pandemic, unfortunately, we had to decrease our scope. So our tool doesn't show your actual stress values. Rather, it doesn't show your actual stress values that we gathered from the FEA models and our calculated models from experimentation. But rather it demonstrates just like that the A to B comparison between the different stresses.
So here we can see the main layout of the main screen of the software tool. The main goal during the design phase was to ensure that it was extremely user-friendly, easy to use, and also interpret. So when a user opens the program up, the first thing they see is the instructions up top there, and these will walk the user through step by step on how it should be ran and what should happen when they're running the calculations. Due to the function of the tool, a local copy of the master spreadsheet must be saved to the user's computer to allow for full functionality. The program flows left to right as all the user buttons are located on the left side of the screen, and the results appear after running the calculations can be seen on the right in table form and also bar graph form. The table on the left displays the data for the current sample being calculated, and the table in the middle displays all previously calculated data for up to 20 samples. It also calculates the minimum stress values that are found during the calculations, so the user can quickly see which geometries give the lowest stress values. And the graph on the right side displays the stress values obtained for each sample in bar graph form to allow for a more visual aspect of what is happening when the root geometries are changed. So on this slide, we see a little bit more of an in-depth detail of what each button actually does. So as I stated before, the buttons on the left side are what the user would use to actually control the program. To open the input window button will allow the user to bring up the root stress calculation window where they will enter in their root fillet radius and also addendum of basic rag values. To begin the calculation, the user will hit enter or click on run calculations. After each calculation, the window will stay open to allow for the user to continuously enter in different parameters to create quick comparison values. The user may exit this window whenever they please. The window below the input window button displays the stress values that were calculated for the current sample and also the values that were entered to obtain it. As stated before, after each calculation, all the previously calculated values will be saved in the table and displayed on the bar graph. If the user would like to export the results to a PDF, they can click the button and it will export both the table and the graph with the user, where they can save it locally to their desktop or wherever they please. When the user is ready to start over, they can hit reset values and all the fields of the Excel spreadsheet will go to 0 and they can start at sample 1 again. There are two sheets to the actual software program. There's the input sheet, as we saw on the previous slide, and there's also the equation parameter sheet where it shows all the calculations that are going on behind the scenes and also allows the user to change parameters such as the load, diameters, load directions, pressure angle, and these can be changed to actually fit the user's specific needs as they please. So for the experimental validation portion of this project, 6 different gear geometry samples were created using Fusion 360. Each of them were designed using all the same dimensional parameters besides the actual root fillet geometry to ensure that the only main variation in between samples during testing was due to these different geometries. The current methods for analyzing the root stresses do not allow for non-tricoidal geometries to be ran without performing full FE modeling. So 3 uniquely designed elliptical shapes were created to validate if the Excel tool was capable of doing what current methods could not. On the right side in the figures here, we can see the top row of the samples use common tricoidal shapes, and the bottom 3 are uniquely designed elliptical shapes.
Like Jacob said, we had 6 samples of uniquely shaped test gear blanks. The rest of the gear test sample was manufactured to kind of mimic the cutoff of a gear. So after these geometries were drawn up in Fusion 360, all of our pieces were sent out to 4 Flutes Machining to be manufactured. So these fixtures were created. So the outside fixture, we had 2 angled outside fixtures and 2 lower blocks at the bottom. So all of these fixtures were created to be designed to be able to clamp down to our load stand to avoid any type of movement during testing when it's being loaded. and to also hold the gear sample without any additional strength added to the test pieces, just so we can make sure our results are reliable. And then we used a variation of bolts and dowel pins to put our fixture all together. So all of our pieces were made of 4140 steel. Then we have down in our bottom right corner our custom low tip that we created. So this was made out of hardened high carbon steel. And this low tip was designed to match the face width of the actual gear tooth to allow a more uniformly distributed load. And this was something that we could manufacture ourselves. So before our testing took place, we had to make sure our instrumentation was all in order. So from our ISO 6336 spec, we noticed that our maximum loads were at our locations D and B on this figure off to the right. So noticing that these were our two main maximum stress points, we got these two locations strain gauged for each of our 6 samples. So after these were strain gauged, we set up the instrumentation in our test cell and began to conduct our testing. So basically our test data was drawn from Canopy, and it gathered our load, our position, and our 2 strains that we strain gauged. These results were used to calculate our maximum bending stress, and we calculated this by multiplying our strains that we gathered by our elastic modulus of this material, which was around 270 gigapascals. So our testing was completed, like we said, at our Eaton Corporation's testing facility, which was located in Galesburg, Michigan, in their test cell 11. So we used the 20 kilopound force hydraulic servo controlled vertical load frame to apply a range of forces from about 1 kilonewton to 20 kilonewton in increments of 5 kilonewton, so 1, 5, 10, 15, and 20. This load was applied at about 10 millimeters from the tip of our front of our gear tooth. And like I previously stated, we gathered our load, our position, and our 2 strain values into Canopy. And then we then pulled all that data into FAMOS, which we used to analyze our data, and later fully gathered all of that data into Excel, where we used to compare our results to our calculated or validate our calculated software.
So to both confirm the results of our experimental testing to ensure that there was not significant experimental errors, and to provide another method to validate the results of our Excel software tool, we completed finite element analysis using the finite element modeling capabilities in ANSYS. We followed the same geometry and load parameters that were used in the experimental testing. We imported the test piece models from Fusion 360. We constrained the back and bottom sides of the test pieces, and then placed a force perpendicular to the tooth face toward the end of the tooth and ran a simulation to analyze the maximum principal stress and view the stress distribution. The picture on the right in this slide shows the results of one of these simulations on a test piece. A high stress concentration can be seen in the root fillet area. For comparison with our other values in this project, we use the highest value of principal stress that this finite element analysis found. So this graph here shows a comparison of the stress values for one of our samples for all 3 of our different methods, the Excel and our 2 validation methods. The values from the finite element model and the experiment are almost exactly the same, while our Excel model values are significantly lower. This was somewhat expected when we were designing our tool. Our Excel tool is currently set up using calculations for root bending stress obtained from ISO and other sources, and it does not use the full finite element modeling equations. and also does not currently take into account the exact geometry of our root fillet, but approximates that root fillet geometry based on only 2 geometry parameters. The tables on the right show our stress values for each different geometry at different loads. So what do these numbers mean? So these bar graphs show the stress values found from all 3 methods for each of our 6 samples side by side. The graph on the left is for a 5,000 Newton applied load, and the graph on the right for a 15,000 Newton load. As was evident in the previous slide, the stress values are lower for our Excel tool than for the validation methods. However, we did successfully predict the directional change in the stress values when switching between different geometries, and also the proportional magnitude of that change is quite similar, though not exact. These results, again, were all obtained just based on 2 simple geometry parameters in our Excel tool. I'll let Jake sum these results up here on the next slide.
So to conclude on a couple things that Nick spoke about in the previous slides, the results obtained from the FEA model in ANSYS and from experimental testing correlated very well with each other and gave confidence in their use as a validation method for the Excel tool. By obtaining very close results from both the FEA model and the experimental portions, this told us that utilizing FEA modeling proves to be a very accurate depiction of what is occurring during real-life scenarios, and that this modeling should be implemented into the software tool. Although the Excel tool did not reach the same level of accuracy as the other 2 methods did, it did show promising results by still accurately depicting the same changes in stress. It still gives the user a good idea as to what geometries will cause an increase or decrease in stresses. This tool does prove to be a quick and efficient process for this optimization process, but some improvements need to be made to fully implement FEA modeling to obtain completely accurate results.
So again, just to sum up some of our next steps and the improvements that need to be made. First, we want to make the tool, again, more finite element based to produce stress values that more accurately reflect actual real-life values. We also want to change our input to allow the user to directly import complete geometries of the root fillet that they want to analyze. This would probably be done via importing a geometry with just XY coordinates. And that would improve the accuracy
joining Jake's presentation
instead of having just a couple of geometry parameters as it's currently set up.
Oh, I thought it was 10:45.
Once the changes and improvements have been incorporated into our Excel tool and the ideal root geometries for minimizing bending stress and maximizing our bending strength of gear teeth has been found, tooling design changes will likely need to be made in order to manufacture these new geometries. Much of this is now becoming possible through various additive manufacturing methods. So what this tool can do that other gear design tools do not, Jake kind of brushed on this earlier, is to compare the stresses generated by many different root geometries and not just standard root fillet shapes that are currently created by Hobbs or other tools that are used to cut gear teeth during the manufacturing process. Again, that analysis cannot easily be done currently without doing full finite element modeling of the gear. So we believe that moving forward, there are great possibilities for this gear design tool.
Again, we want to thank everyone for your time and attention during this presentation, and we just want to open up the floor for questions.
Thank you, everybody. Especially for presenters. This is the time to ask the questions. Either you can, of course, type your question on the chat room, or you can, of course, unmute your mic and ask question directly, please. So this is the time. So meantime, maybe each of you will answer me. So what are the main challenging part doing this project during this time?
Some of our main challenges were kind of being hit with the pandemic, so there was a lot of times when um, we couldn't meet up, and then when the shutdown happened, there was a lot of times that we had to push our testing back or push our getting our pieces manufactured back. So just for like the experimental portion, we faced a lot of kind of roadblocks, and then looking at availability for the cell when a lot of tests were coming back on like in availability. So those were a couple of roadblocks that we faced during this time.
Thank you. So anybody has any questions to this group, please? Okay, guys, so I didn't see any question in the chat room or anybody asking. Thank you for the presentation once again. Our next presentation will be at 11 o'clock, so 11 a.m. Thank you, everybody.